kind of a description of something. Yes?
Since, with the force in relationship to displacement, wouldn't there be a kind of area component since you have force equal to mass times acceleration? Because then if you're calculating the mass, you use density and volume.
Yes, but let me just finish this, and maybe I can answer your question by doing more than I've done just jumping around here at the moment. Let me be specific what's meant by stress, and then we'll come. Maybe I can answer your question after that easier. So let's talk, because the concept is one that's important to get to here. And you're familiar with forces and quantities that are related to the quantity called stress, because fluids do this in part of the problem. You know that from fluids, where that there's the swimming pool effect. If you start at some position and you drop yourself down into a pool, the pressure increases. And what that means is there's forces that are applied, like to your eardrum, right? That's your area effect. Pressure is always given as units as force per unit area. So pounds per square inch, if you like American units, or newtons per square meter, if you're in SI units. It's not kilograms. What is it? It's a stupid unit. You see people use like kilograms per square meter. That's not that's not a proper unit, right? Because kilograms are a mass unit. But newtons per square meter, that's a quantity called a Pascal. That's a pressure unit. And it's, as you go down in a fluid, pressure increases. So it's force over area. That is part of the quantity we're talking about. I can't remember the next slide. That means that pressure is what's often referred to as a surface force. So the forces are acting across some area. And when that fluid is not in motion, all those forces are balanced. Remember I said fluids are something that cannot, all the forces can't be imbalanced. It'll just keep flowing until it runs out of a driving force. So there's no imbalanced forces in the material, it just stops. That means when it's stopped, you're on the bottom of that graph, of that Newtonian fluid graph, and all the forces are balanced. In that particular case, you have uniform pressures in all directions. That's one way of thinking about what stress is, then. That's non-differential stress. The pressure is uniform in all directions. In fluid, actually, the instant you add a different component to that, though, the material starts to float. In solids or a moving liquid, or fluid, it's differential stress that drives the deformation. A difference between pressure, so there's a directional property to that force. So there's more forces in one direction versus another that make up that particular quantity. That's what stress is. There are two components to stresses. One of them is the pressure term we just talked about, and that's referred to as normal stress. In a normal stress, when you have normal stresses, the forces that apply to the surface elements are perpendicular to that particular surface. And so by Newton's third law, every force on that side of that cube is counterbalanced by one on the other side if the material is not in motion. So if it's in static equilibrium, they're in perfect balance on either side of the cube, those normal forces. There are two ways that can be represented. They can be under compression. So the vectors, the forces are towards each other or directed towards each other across this little cube, if you will. Or they can be outwards, in which they're tension. There are different sign conventions that are used for this, which confuses people. Such that in some cases people use tension as positive and sometimes they use compression as positive. Just be aware of this particular thing. We'll get to that as we go along. Engineers like positive compression. The other type of load that can be applied to a material is called a shear stress. A shear stress is just a component of the load that's applied to the margins of the system. That's the dynamic equivalent of the strain effect we talked about, simple shear. So it's shear stress loads that cause material to deform in shear. Those components, though, it turns out that what's odd about stress, I'm jumping around here. I'm running out of time. Afraid of that. I mentioned this a moment ago. It's shear stresses that drive deformation. And so, like, for example, in viscous fluids, it's the shear stresses that are dissipated to produce normal stresses only, that dissipate differential stresses within a material. But all materials possess, or any material that's under a differential stress turns out to have both shear stresses and normal stresses. And it's the essence of what the quantity stress actually is. Now I'm jumping around in a bunch of different directions. Let me come back to them for a second, what stress really is. And this is just a figure I stole out of that Wikipedia site. Nice figure that shows the point. There's a, what's it called, Cauchy's stress theorem or something like that. It states, here's what's the way of describing what stress is. Here are three coordinate axes, x, y, z, right? x1, x2, x3. There's a body that's undergoing loads in different directions. So this body has a differential load, say, in one direction versus another. Cauchy's stress principle says that for any surface element within this body that's under a differential load, there exists on that surface element a load, or a finite load, that's a force that's applied across that surface element. And in the limit, as that surface area shrinks to zero, so it's classic calculus problems, you get to infinitesimal size, that quantity does not vanish. It stays a finite quantity. There's a finite load that comes across that is applied across that little surface element as you get to smaller and smaller position. That's the quantity called stress. That's what stress is. But what does that mean, what it represents? This is sort of an abstract concept, so let me say it a different way. I said quantities called second-order tensors are quantities that take two vectors to describe them. We kind of showed that, like, in the case of strain, it was related to the gradient of a displacement field, or two vectors that were involved. Here it's more clear what the two vectors are, and hopefully this will make sense when I get done here. The two vectors that are involved are the force that's applied to that surface element that doesn't vanish, which is called the traction, by the way. So there's a force vector that's applied to the surface element, and the other vector is the orientation of the surface itself. There's a vector that describes the orientation. So the orientation of that surface in space is one vector. The other vector is the force that's applied to that surface. So there's two vectors involved. One is the orientation vector, and the other is the force vector that's present, that's still left over on that particular surface. What that doesn't say is that there's an infinite number of surfaces that are reference surfaces then, right? That you could consider in this context. You can rotate that reference surface any way you want, and there will be a value, there'll be a finite value for every surface element. There will be a finite value for that traction across that surface. They might be pure pressures or pure normal, or there are some combination of the two, with a component that's a shear component or and a normal component across them. But every different surface will be different, right? You can imagine you have a large pressure in this direction, there's going to be a large normal stress in this direction. But if you're pulling something in this direction, then you're going to have a large tensile stress in this direction. There's a directional property, and that directional property is related to this vector, right? That's a long-winded way of saying that y stress is what's called a second-order tensor because it has this two directional properties, the surface element that you're interested in and its orientation. Actually, how does that relate to something geologic, right? A geologic example might be a fault plane, which has orientation in space, and there are loads across it. And you want to know what the relative amounts of shear versus normal stress are across that plane related to this problem. And so there's two different quantities, force and area is a quantity you don't think of as a vector, but it is a vector. I'll finish this quickly and talk about the way that's quantified is summarized in this slide, and didn't want to write all this on the board and everybody just sit there and say, I don't know what that's about. To make a long story short, go through this derivation and you'll all just say, what the hell is that about? You could think of this, here's what this is related to, or one way to think about it. You can imagine an infinitesimal cube that's superimposed on a set of coordinate axes, x, y, and z. Now the cube has reference to the coordinate axes of the reference coordinate system. Remember I said coordinate systems are arbitrary choice. This quantity is a physical quantity, so that I stick the coordinate system in and superimpose it onto a physical quantity. If this were a vector field and I had this coordinate system to it, it would have components x, y, z, right? But I now stick this quantity into this coordinate system. It now has directional properties. And so it has three different faces that describe, it would take three faces to describe that quantity completely. Three faces to that cube. On this side, I have loads. On this side, I have loads. And on this side, I have loads. And there's counterbalancing forces on the backside of the cube from Newton's third law. That gives rise to 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. Got a little thread number. 9 terms that describe that particular quantity in 3 dimensions. 3 components on each face and a reference direction for each face. And that could be represented as a set of 3 equations, where this is the traction across this face that's perpendicular to that face. This is the traction that's perpendicular to that face, or it's that face that's perpendicular in that direction. This is the traction that's on that face or perpendicular to that direction. That gives 3 components, which are given by these quantities as often shown by the notation sigma, 1, 1, 1, 2, 1, 3, and so forth, 9 different terms. And that's a good place to stop. Next time, I'll pick this up a little further and talk about this quantity. Just to give you a thought on this, the coordinate system is arbitrary, right? So there always exists 9 terms, just like in a vector always has 3 in 3 space. But if you turn the coordinate system, those values change. And they follow a specific set of laws, and there are specific geometric elements of that have analogs to strain. We'll get to that next time, because that's enough for you.
Can you go back a slide?
Sure.